Let's return to this example of the cricket chirps. This is a simple linear regression model. We can see we have a lot of output here. Right? You can see at the top here, right, the statistical software reminds us of the code that we typed in to run this regression model. This is always good to double check to make sure that you have your outcome and input or predictor variable coded and set appropriately. The important part with simple linear regression, in contrast to, for example, correlation or covariance, is that the outcome variable matters. Right? If you switch what you label y and what you label x in simple linear regression, you're going to get different coefficients. It means something different to predict Fahrenheit degrees using cricket chirps rather than predict cricket chirps using degrees Fahrenheit. In contrast with correlation, if you switch those two variables, it's not going to make a difference. So it's always a good idea to make sure, if you're intending to predict degrees Fahrenheit, make sure that you set up and typed into the statistical software that you really are predicting degrees Fahrenheit. So in this case, degrees Fahrenheit is our outcome variable y, and cricket chirps per minute is our input or predictor variable x. We want to use cricket chirps per minute to predict the temperature in degrees Fahrenheit. Then you can see below this, right, we also have the distribution of residuals or errors. Right, this output, right, tells us the residuals for each of the observations in the data set. So we have 7 observations, and so we can see we have 7 different rows of our data set. We have 7 different y values, but we also have 7 different x values. We also have 7 different residuals. Right? The residual or error for each observation is simply y minus y hat, where y hat is derived from the simple linear regression model. And so we can see how far each of our observations lie above or below the line. For larger data sets, the output will give summary statistics of the residuals here. But since we only have a data set of 7 observations, rather than providing us with summary statistics, the statistical software conveniently gives us our entire set of residuals. Residuals are often useful because you can use this information to watch out for outliers. If one of these residuals is very large, we might consider refitting our regression model or trying to see if there's a coding error for that one particular observation. So it's a good idea to check our residuals. We'll talk more about that later. But for now, just keep in mind that's what the statistical software is telling us. Then you can see that we are given the point estimates and interval estimates, or inferences. So here we have the standard errors for each of the coefficients, the test statistics, or t-ratios. We also have p-values for our regression coefficients. So let's look at these 2 coefficients, the intercept and cricket chirps. So we're given 2 rows. Right? That first row gives us all the information regarding the intercept, sometimes known as the constant. Right? It's synonymous. If somebody says, what's the constant in your model? Well, they're talking about the intercept. Right? That's all it means. We also have a row for point estimate, standard error, t-ratio, and a p-value for this slope, for our input variable, cricket chirps. Right. Then you can see here that we have point estimates for the intercept and cricket chirps. The point estimate, right, it's just our best guess for the population intercept, and it's our best guess for the population slope from this sample. So this is just, if you were just to look at the sample estimates, just run a simple linear regression on the sample, you would get these 2 values. But these are, in absence of additional information, our best guess for the population intercept is our sample intercept. In absence of additional information, our single best guess for the population slope is our sample slope. These are the point estimates. And so we see that the slope in the sample is roughly 37.68. The intercept in the sample is roughly 37.68, and the slope is roughly 0.23. From these 2 values, we can construct our fitted regression line in the sample. Right. We also have test statistics. Right. Here we have a test statistic, or t-ratio, for the intercept. And we also have a test statistic, or t-ratio, for the slope. Recall that we index our coefficients using j, where k equals the total number of inputs in our model. Here we have k equals 1 because we have 1 input. We have 1 x variable in our model. And we have 2 coefficients. When j equals 0, that refers to, that's an index for the intercept. When j equals 1, we are referring to the slope. So for each of these two rows, the intercept and slope, we have a t-ratio. And that is simply our point estimate divided by the standard error for that particular coefficient. Where this, and the key point here is that implicitly we're subtracting out the null. The null is 0 in both cases, so we don't have to include it. What these t-ratios are telling us, they're telling us how far, right? They're giving us sort of a standardized measure of how far our sample, how far these sample coefficients lie from the null hypothesis. The greater, the larger this difference, right, in absolute value, the more inconsistent our sample is from the null hypothesis. When we have inconsistency, we're more likely to reject that null hypothesis. It's very unlikely to obtain these particular sample coefficients under the assumption that the null is true, under the assumption that these coefficients are 0 in the population. So we have these two t-ratios. They're both test statistics. They each lie on a t-distribution governed by n minus k minus 1 degrees of freedom. So since our sample size is 7, we have one input in our model, so we have one x variable. We have 7 minus 1, so we have 5 degrees of freedom. That's the effective sample size when we're conducting these inferential tests. For each of these t-ratios, or test statistics, we are also given p-values. These are probability values just like before. These are the p-values based on where these t-ratios lie on the t-distribution with 5 degrees of freedom. So we can see that for the intercept, the probability of obtaining a test statistic as or more extreme than the one we obtained under the assumption that the coefficient is 0 in the population is almost 0. The p-value is very low. It's below our alpha level of 0.05. For the slope, the p-value is also very low. It's almost 0, and of course it is below our alpha level of 0.05. So in both instances, we reject the null that the coefficient for the intercept and the coefficient for the slope in the population is equal to 0. To put it another way, we say, we don't think that we are finding a statistical artifact. This is not just due to random sampling variability. When we treat these 7 observations as a random sample from a population, it's not due to random sampling variability. There is something real going on in the population, we think, based on this sample of data. Now, the statistical software gives us additional output. These are these little asterisks, sometimes called stars. This is a guide for interpreting the output using a range of alpha levels. So far in this class, we've really focused on using this conventional level of alpha equals 0.05, but the nice thing about a p-value is that you can compare that p-value to a range of levels of alpha, and that's what the statistical software is doing for us right here. So the coefficients are given annotations based on a comparison of different alpha levels, these alpha criterion levels, which are called here in the statistical software output, they're called significance codes, referring to the fact that you have different levels of statistical significance. And we're given annotations for different levels of alpha. So we're given an annotation for alpha equal to 0.001, 0.01, 0.05, and alpha equals 0.1. The output does not provide annotations if the p-value is greater than alpha 0.01. It's very rare to see an alpha criterion level used in research studies that is actually larger than alpha of 0.01. Typically you see 0.05, sometimes you'll see 0.1, often you'll see 0.01 as well. So let's go over what these annotations are really telling us. So we have these different significance codes. These are different annotations for different levels of alpha. So the idea is that it's a range of alpha levels from 0 all the way up to 1. Okay, we can interpret these as follows. For alpha equals 0.001, right, if the p-value is less than or equal to alpha 0.001, then the output is annotated with 3 asterisks. So provide the p-value with those 3 asterisks. And so all you need to do is, you don't even need to compare that p-value to level of alpha. You can look at that p-value and say, oh, there are 3 asterisks. I know that it's statistically significant at the alpha 0.001. I can reject the null using that level of alpha. For alpha equal to 0.01 as the criteria level, if the p-value is less than or equal to 0.01, then the output is annotated with 2 asterisks. So it'll annotate that p-value for that particular coefficient with 2 asterisks. Again, you can just look at the p-value, look at those 2 asterisks and say, oh, that's statistically significant at the alpha 0.01 level. I can reject the null at that level. For alpha equals 0.05, if the p-value is less than or equal to 0.05, then the output is annotated with 1 asterisk. For alpha equals 0.1, if the p-value is less than or equal to 0.1, then the output is annotated with a single period. So you can see that it's providing us a range of annotations to help us interpret the p-value. So we don't have to go through the mental calculation of saying, well, is that less than or equal to 0.05 or 0.1? You can just look at the annotations. You can just say, well, that is 3 stars next to it. That's statistically significant at the alpha 0.001 level, and so on and so forth. So let's look at this in context. Okay, so here we are given the p-values, and you can see that we have these asterisks. Both lines are, in fact, annotated. Right? The intercept has 3 asterisks. It's annotated. Its p-value is annotated. And the variable chirps, its slope, is also annotated in terms of its p-value. So since the p-values for both are very low, right, they're both well below alpha 0.001. And they're both annotated with 3 asterisks, meaning we can say they're statistically significant at the alpha 0.001 level. Right? Keep in mind, if a p-value is statistically significant at the alpha 0.001 level, it's also statistically significant at the 0.05 level, the 0.01 level, the 0.1 level. It's statistically significant at higher levels of alpha. So that's why we only need that one bit of annotation to make that conclusion about 0.05 as well. Meaning, since both of these coefficients are statistically significant at the alpha 0.001 level, we also know that they're statistically significant at the alpha 0.05 level, meaning we can reject the null hypothesis that the coefficients in the population are equal to 0 at the 0.05 level, but also at the 0.01 level. The statistical software also gives us a measure of model fit, known as the root mean square error. The idea behind the root mean square error, it's sometimes called the residual standard error. Intuitively, it's the average size of the residuals. Right? So each of our observations, they have different residuals or errors. For one person, they might lie fairly close to that regression line. Another person might lie really far away. But to get an idea of the overall model fit, how close the line fits to the data, it's useful to take, in essence, an average size of these residuals. Calculate what's the average residual, average error, across all of these different observations. Well, that's what the root mean square error is telling us. It's computed by taking the square root of the sum of the squared errors and dividing by the degrees of freedom. So where the degrees of freedom is n minus k minus 1. We're also given this measure of model fit that is r squared, sometimes called the coefficient of determination. This is the proportion of the variation in the outcome accounted for, explained by our regression model, by our input variable. Sometimes you'll see the output in statistical software programs refer to something called adjusted r squared. Adjusted r squared is just a slightly different version of r squared that adds a penalty, or sometimes called a correction factor, for including a noisy input into the model. The basic idea is that sometimes you can include junk variables into a regression model, and the r squared will increase regardless, even though these variables aren't adding much predictive value to that model. Therefore, sometimes people like to report adjusted r squared, which penalizes including these kinds of noisy variables. Adjusted r squared will never be greater than r squared. It's always going to be equal to or less than r squared. For the purpose of this course, we really just want you to focus on r squared and intuitively understand that it's just giving you an idea of how much variation in the outcome is accounted for, explained by our regression model. In this case, since we have one input, it's really telling us how much of the variation in the outcome is accounted for by one variable, that variable cricket chirps. Higher level r squared indicates a greater proportion of the variation is explained by the input variable. The output also gives us something called an Ftest for the slope. Right? This is an inferential test based on the Ftest statistic, which lies on the F distribution. Intuitively, the idea is that with a simple linear regression, the Ftest can be used as an alternative to the t-test for the slope, with the null that the population slope equals 0 versus the alternative that is not equal to 0. The Ftest statistic, it lies on the F distribution with a certain degrees of freedom based on the number of input variables. Right? The simple linear regression model, k equals 1. Right? The basic idea, though, is that the Ftest statistic is just a different way of conducting an inferential test on the statistical significance of that slope. We're going to focus in this course more on the test statistics, but I just want to point out that it's nothing mysterious. It's just giving you additional information about the inferences in your regression model. In addition, we can see that we're also given a confidence interval. It's always a good idea to compare your regression results to a confidence interval. So here we have a 95% confidence interval, right? And we have a confidence interval for the intercept and for the slope, for that variable chirps. And here you can see that we're 95% confident that the true regression slope for chirps is between 0.19 and 0.267 roughly. Right? We're 95% confident that the true intercept in the population is between 32.6 and 42.76 approximately. This is just like before with the correlation coefficient or the other inferential tests we've conducted. Confidence interval is interpreted in this very similar way. And with that, we will explore additional avenues for looking at linear regression and inferential statistics.